You know what's fascinating? Right now, as you're listening to this, there's a technology that can write poetry, debug code, explain quantum physics, and even create entirely new recipes, all in a matter of seconds. But here's what nobody's really talking about. These AI systems don't actually understand a single word they're saying. Not in the way you and I understand words. And that paradox, that fundamental contradiction at the heart of artificial intelligence, is what we're going to unpack today. Because once you understand how large language models truly work under the hood, you'll never look at AI the same way again. You'll start seeing the invisible patterns, the elegant mathematics, and yes, even the profound limitations that shape every interaction you have with these systems. I'm going to take you on a journey today that goes far beyond the surface-level explanations you've probably heard. We're not just going to talk about what LLMs are, we're going to explore the cognitive architecture that makes them possible, the philosophical questions they raise about intelligence itself, and the practical implications that affect how you should actually use these tools. By the end of our time together, you'll have a mental model of AI that most people in the tech industry don't even possess. So let's dive deep. Let me start with something that might sound counterintuitive. When you ask ChatGPT a question and it gives you this perfectly coherent, seemingly thoughtful response, what's actually happening isn't thinking in any traditional sense. It's pattern completion at an almost unimaginable scale. And understanding this distinction is absolutely crucial. Think about how you learned language as a child. You didn't memorize probability distributions. You experienced the world, formed concepts, connected those concepts to words, and gradually built an internal model of reality that language helps you navigate. Large language models do something that looks similar from the outside but is fundamentally different on the inside. They've ingested billions upon billions of text examples and learned the statistical relationships between words, phrases, and ideas. They've become extraordinarily sophisticated at predicting what word should come next in a sequence. But here's where it gets interesting. Even though these models are just doing next word prediction, the complexity of that task when performed at scale actually requires them to learn representations of meaning, context, and even logical reasoning, at least in a functional sense. It's like how a chess computer doesn't need to want to win to play brilliant chess. The objective function of predicting text accurately has forced these models to develop internal mechanisms that mirror aspects of human cognition, even without conscious experience. This creates what I call the intelligence paradox. These systems can solve problems they were never explicitly trained to solve. They can translate between languages they never studied together. They can reason through multi-step logical problems by maintaining context across thousands of words. Yet ask them to truly understand what a color looks like, or what sadness feels like, and they're simply manipulating symbols they've seen associated with those concepts millions of times. Now let's talk about how these systems actually come into being, because the training process reveals so much about their capabilities and limitations. Imagine starting with a neural network, essentially a mathematical function with billions of adjustable parameters, that's been initialized with random values. At this stage, if you ask it to complete a sentence, it will produce absolute gibberish. Random characters, nonsensical word combinations, complete chaos. The training process is essentially about exposing this random system to enormous quantities of text and gradually adjusting those billions of parameters to minimize prediction error. Every time the model predicts the wrong next word, the training algorithm calculates how wrong it was and slightly nudges all those parameters in directions that would have made the correct prediction more likely. This happens trillions of times across the entire training dataset. What's remarkable is that this relatively simple objective, predict the next word accurately, turns out to be an extraordinarily rich learning signal. To predict text well across diverse topics, the model needs to learn grammar, factual knowledge, reasoning patterns, even something resembling common sense. It needs to track context across long passages. It needs to understand when someone's being sarcastic versus literal. All of this emerges from the pressure to minimize prediction error. But here's a crucial insight that most explanations miss. The training process has multiple distinct phases, each serving different purposes. The initial pre-training phase, where the model learns from vast amounts of unlabeled text, gives it broad general knowledge and language understanding. But that's just the foundation. Modern LLMs go through additional fine-tuning phases where they learn to follow instructions, engage in dialogue, and align with human preferences and values. This fine-tuning is often done through a process called reinforcement learning from human feedback. Human evaluators compare different responses the model generates and indicate which ones are more helpful, harmless, and honest. The model then learns to increase the probability of generating responses similar to the preferred ones. This is how we get from a system that just predicts text to one that feels like a helpful assistant. There's also something called in-context learning that deserves attention. Once an LLM is trained, it can actually learn new tasks from just a few examples provided in the prompt itself, without any parameter updates. You can show it 3 examples of sentiment analysis and then ask it to analyze a 4th piece of text, and it will often succeed even if it never explicitly trained on sentiment analysis. This suggests these models have developed meta-learning capabilities. They've learned how to learn from context. Let me introduce you to perhaps the most important innovation that made modern LLMs possible: the attention mechanism. This is where things get really interesting from an architectural standpoint, and understanding it will completely change how you think about what these models are doing. Before attention mechanisms, earlier neural networks processed text sequentially, word by word, trying to compress all the relevant information from previous words into a fixed-size memory. This created a fundamental bottleneck. Imagine trying to summarize an entire novel into a single paragraph and then using only that paragraph to predict what happens next. You'd lose crucial details, especially from earlier in the text. Attention mechanisms solve this by allowing the model to dynamically focus on different parts of the input text when processing each word. When the model is trying to predict the next word, it can assign different importance weights to every previous word, essentially asking, which previous words are most relevant right now? This happens through a mathematical process where the model learns to compute similarity scores between different positions in the text. The real breakthrough came with self-attention in transformer architectures. Instead of just attending from output back to input, every position in the text can attend to every other position simultaneously. The model creates multiple attention heads. Think of them as different ways of looking at the relationships between words. One head might focus on grammatical dependencies. Another might track thematic connections. Another might identify SEO references, figuring out that it, in one sentence, refers to the cat, mentioned several sentences earlier. What's profound about this is that attention mechanisms allow the model to learn its own notion of relevance. During training, it discovers which patterns of attention help it make better predictions. Some attention heads learn to identify subject-verb relationships. Others learn to connect questions with relevant context earlier in the passage. The model essentially learns how to route information through its layers in task-appropriate ways. This also explains why modern LLMs can handle such long contexts, tens of thousands or even hundreds of thousands of words. The attention mechanism gives them a way to maintain access to all that information without bottlenecking it through a fixed-size memory. They can reach back and grab specific relevant details when needed, rather than trying to compress everything into a single representation. Now I want to talk about something that sounds technical but is actually quite beautiful: embeddings. This is how language models actually represent the meaning of words in a way they can mathematically manipulate. And understanding embeddings will give you deep insight into both the power and the limitations of these systems. Here's the core idea. Each word or token gets converted into a vector, basically a list of numbers, typically hundreds or thousands of them. What makes this powerful is that words with similar meanings end up with vectors that are close together in this high-dimensional space. The word king and queen would have similar vectors. Happy and joyful would cluster together. Run, sprint, and dash would occupy nearby regions. But it goes deeper than simple similarity. These embedding spaces capture relational structures. There's a famous example where you can take the vector for king, subtract the vector for man, add the vector for woman, and end up very close to the vector for queen. The embedding space has learned that the relationship between king and queen is analogous to the relationship between man and woman. This isn't programmed in, it emerges from the training process. By learning to predict words in context, the model discovers that it needs to organize its internal representations in ways that capture semantic relationships. Words that appear in similar contexts get pushed closer together. Words that play analogous grammatical roles develop parallel structures in the embedding space. What's fascinating is that these embeddings don't just capture simple associations. They encode subtle distinctions, contextual meanings, even emotional valences. The same word can have different embeddings depending on context. The model learns contextual representations where bank in river bank gets a different vector than bank in savings bank. This embedding approach also explains why LLMs can perform zero-shot transfer across domains. Since concepts are represented as positions in a learned semantic space, the model can leverage its understanding of relationships in one domain to make inferences in another. It might never have seen a specific question about, say, applying thermodynamic principles to economic systems, but the spatial relationships between concept embeddings allow it to make reasonable connections. However, there's a limitation here worth noting. These embeddings capture co-occurrence patterns and distributional semantics, how words appear together in text, but they don't capture grounded meaning. The model knows that hot and cold are opposites based on how they're used in language, but it has no experiential knowledge of temperature. This is why LLMs can be so impressive with abstract reasoning while sometimes failing at tasks that require physical intuition or sensory understanding. Let's walk through what actually happens when you type a prompt and hit enter. The inference process, how the model generates a response, is its own fascinating dance of computation, and understanding it will help you become much better at crafting effective prompts. First, your input text gets tokenized. This means it's broken down into tokens, which might be whole words, parts of words, or even individual characters depending on the model's vocabulary. A sentence like, "I'm learning about AI," might become tokens like, "I am learning about AI." Each token then gets converted into its corresponding embedding vector. These embeddings flow into the first layer of the transformer architecture. Here, the attention mechanism kicks in, computing which tokens should attend to which other tokens. The output of each attention head gets processed through what are called feed-forward layers, dense neural networks that transform the representations. Then this whole process repeats through multiple layers, typically dozens of them in modern LLMs. What's happening across these layers is hierarchical processing. Early layers tend to learn surface-level patterns, basic grammar, common phrases. Middle layers develop more abstract representations, syntactic structures, entity recognition. Later layers handle high-level reasoning, integrating context, and preparing for output generation. Information flows upward through these layers, getting progressively more abstract and task-specific. At the final layer, the model produces a probability distribution over its entire vocabulary, basically a score for every possible next token. But here's where it gets interesting. The model doesn't just pick the highest probability token every time. That would make the output deterministic and often repetitive. Instead, there's a sampling process. Temperature is a parameter that controls randomness. A low temperature makes the model mostly pick high probability tokens, leading to safe, predictable outputs. A high temperature increases randomness, making the model more creative but also potentially more chaotic. There are also techniques like top K sampling, where the model only considers the K most likely tokens, and nucleus sampling, which considers the smallest set of tokens whose cumulative probability exceeds a threshold. This sampling process happens one token at a time. The model generates one token, appends it to the input, runs the whole process again to generate the next token, and continues until it produces an end-of-sequence token or reaches a length limit. This auto-regressive generation is why longer outputs take more time. Each token requires a full forward pass through the entire model. Understanding this process reveals why certain prompting techniques work. When you provide examples in your prompt, you're literally shaping the probability distributions for subsequent tokens. When you ask the model to think step by step, you're encouraging it to generate intermediate reasoning tokens that then influence the final answer tokens. The context you provide directly affects the attention patterns and thus the entire generation process. Not all large language models are created equal, and understanding the landscape of different model types will help you choose the right tool for specific tasks. The AI ecosystem has evolved into a diverse family of models, each with distinct characteristics and optimal use cases. Base models, sometimes called foundation models, are trained on broad, general-purpose datasets. They're like intellectual generalists, they have broad knowledge but aren't optimized for any particular task. If you've ever interacted with a base GPT model without fine-tuning, you've probably noticed it just continues whatever text you give it. Feed it the beginning of a story, and it'll write more story. Give it code, it'll write more code. It's fundamentally a completion engine without specific instruction following behavior. Then we have instruction-tuned models. These have been fine-tuned specifically to follow instructions and engage in dialogue. They've learned patterns like, when a user asks a question, provide an answer, rather than just complete this text. This fine-tuning dramatically changes the user experience. Instead of a text completion tool, you get something that feels like an assistant. Most consumer-facing AI systems like ChatGPT, Claude, or Bard are instruction-tuned models. There's another category worth understanding: models fine-tuned for specific domains. These start with a general foundation but receive additional training on specialized data. A medical language model might be fine-tuned on clinical notes, research papers, and medical textbooks. A legal LLM gets trained on case law, contracts, and legal documents. A coding assistant trains on vast repositories of source code and programming documentation. The advantage of specialized models is they develop deeper expertise in their domain. A medical LLM will know rare disease names, drug interactions, and clinical reasoning patterns that a general model might miss. But there's a trade-off: specialized models sometimes lose capability outside their domain. They've learned to prioritize certain patterns over others. We're also seeing emergence of mixture of experts architectures. These models essentially contain multiple submodels, or experts, each specialized for different types of tasks. When processing input, a gating mechanism dynamically routes tokens to the most relevant experts. This allows scaling up model capacity without proportionally increasing computational cost for every single inference. Then there's the distinction between open and closed models. Closed models like GPT-4 or Claude are accessible only through APIs. You can use them but can't see their weights or architecture details. Open-source models like Llama, Mistral, or Falcon have publicly available weights. You can download them, inspect them, modify them, and run them on your own hardware if you have sufficient computational resources. Each approach has merits. Closed models often represent the cutting edge in capability because their developers can invest massive resources without worrying about competitors immediately copying their work. Open models democratize access, enable research transparency, and let organizations maintain data privacy by running models locally. The ecosystem needs both. Now let's talk about something immediately practical: how to actually get better results from these systems. Prompt engineering isn't just about being polite to the AI, it's about understanding the model's inference process and crafting inputs that guide it toward high-quality outputs. First principle: specificity matters enormously. Remember, the model is generating tokens based on probability distributions shaped by your prompt. Vague prompts create wide probability distributions. The model isn't sure what style, format, or depth you want. Specific prompts narrow those distributions, steering the model toward your desired output space. Instead of asking, "Write about climate change," try, "Write a 5-paragraph explanation of how carbon dioxide acts as a greenhouse gas, suitable for a high school student with basic chemistry knowledge, using at least 2 real-world examples and avoiding political controversy." See the difference? You've specified length, technical level, audience, structure, and constraints. Second principle: leverage the model's training structure through format prompting. These models have seen countless examples of particular formats during training: step-by-step tutorials, Q&A pairs, pros and cons lists, code documentation. When you structure your prompt in a familiar format, you're activating learned patterns that guide generation. For analytical tasks, try prompting like, "Let's analyze this step by step. First, second, third." The model has seen this structure thousands of times and knows to generate systematic, organized reasoning. For creative tasks, prompts like, "Here's a story outline," "Setting, conflict, resolution," tap into narrative structures the model knows well. Third principle: chain of thought prompting for complex reasoning. Instead of asking for just the final answer, explicitly request intermediate reasoning steps. Think through this problem step by step. Showing your work often yields dramatically better results than, "What's the answer?" This works because generating intermediate reasoning tokens provides the model with context it can then condition on for subsequent tokens. There's a related technique called self-consistency. Generate multiple reasoning paths for the same question, then look for consensus among the answers. If you ask the model to solve a problem 3 different ways and all 3 approaches converge on the same answer, you can be more confident in the result than if you'd only generated one response. Fourth principle: provide examples when possible. Few-shot prompting. Giving the model 2 or 3 examples of input-output pairs before your actual query dramatically improves performance on specialized tasks. The model uses those examples to calibrate its output distribution. This is especially powerful for tasks with specific formats or unusual requirements. Fifth principle: use system messages and role-playing strategically. Many chat interfaces let you set a system message that persists across the conversation. You can use this to establish expertise level, response style, or domain focus. You are an expert mechanical engineer specializing in automotive design, will bias the model's responses differently than you are a science educator explaining concepts to curious students. But there's a counterintuitive insight here: sometimes less instruction is more. If you over-constrain the model with too many requirements, conflicting instructions, or excessive detail, you can actually degrade output quality. The model has to balance competing objectives and might satisfy none of them well. Find the minimum viable specificity that achieves your goal. Let me also address common pitfalls. Don't anthropomorphize too much. Saying "please" and "thank you" doesn't hurt, but the model isn't actually experiencing politeness. You're just adding tokens that might slightly affect probability distributions. What matters more is clarity and structure. Avoid ambiguous pronouns and references. The model tracks context through attention mechanisms, but it can lose thread in complex conversations. Instead of, "Can you explain how it works?" after a long discussion, try, "Can you explain how transformer attention mechanisms work?" Explicit references reduce ambiguity. Finally, understand that iteration is part of the process. Your first prompt rarely produces optimal results. Treat prompt engineering like a conversation where you're gradually calibrating the model's understanding of what you want. Start broad, then refine based on what you get back. Let's move beyond abstract understanding and talk about what these systems are actually transforming in the real world right now. Because once you look past the hype and the headlines, LLMs are creating genuine practical value in domains most people haven't even considered. In software development, we're seeing a fundamental shift in how code gets written. These models serve as intelligent autocomplete on steroids. Developers describe what they want in natural language or write a function signature, and the model generates implementation code. But it's more than just boilerplate generation. These systems help debug by analyzing code and suggesting fixes. They explain unfamiliar codebases by generating documentation. They translate between programming languages, helping developers work across technology stacks. What's remarkable is how this changes the learning curve for programming. Beginners can describe what they want to accomplish conversationally and get working code they can study and modify. Expert developers can stay in flow state, offloading routine implementation details to AI while focusing on architecture and business logic. The craft of programming is shifting from pure syntax mastery toward higher-level problem decomposition and AI collaboration. In education, LLMs are becoming personalized tutors available 24/7. A student struggling with calculus can get explanations tailored to their level, work through practice problems with step-by-step guidance, and receive immediate feedback. The system adapts to their pace, rephases concepts in different ways if they're confused, and draws connections to topics they already understand. But the educational applications go deeper. These models can generate customized practice problems, create study guides from textbook chapters, simulate historical figures for immersive learning experiences, and even help teachers design lesson plans and rubrics. We're moving toward truly personalized education at scale, something that was previously only available to students wealthy enough for private tutoring. In content creation, LLMs are powerful collaborators. Writers use them to overcome blank page paralysis by generating first drafts they then refine. Marketers create multiple variations of copy for A/B testing. Journalists use them to quickly synthesize research from multiple sources into initial article structures. Social media managers generate engaging post variations for different platforms. The key insight is that professional creators rarely use raw AI output directly. Instead, they treat these models as intelligent first draft generators or brainstorming partners. The human remains in the loop for quality control, fact-checking, adding nuance, and ensuring the content resonates authentically. But the AI handles the grunt work, dramatically accelerating content production timelines. In customer service, LLM-powered chatbots are finally crossing the threshold from frustrating to genuinely helpful. Unlike rigid rule-based systems, these models understand natural language variations. Customers can describe problems in their own words without searching for specific keywords. The systems maintain context across multi-turn conversations and can handle complex queries that require synthesizing information from multiple sources. Advanced implementations go further. They can analyze customer sentiment during conversations and escalate to human agents when detecting frustration. They provide agents with suggested responses and relevant information in real time. They automatically generate conversation summaries for record keeping. The result is faster resolution times, more consistent service quality, and freed up human agents to handle genuinely complex issues. In healthcare, we're seeing early but promising applications. LLMs help synthesize patient records, highlight potential drug interactions, suggest differential diagnoses based on symptoms, and draft clinical notes from doctor-patient conversations. They can explain complex medical information to patients in accessible language. In research contexts, they help scientists stay current with rapidly expanding medical literature by generating summaries of new papers and identifying relevant studies. Critical caveat: these systems augment healthcare professionals rather than replace them. A doctor makes final diagnostic and treatment decisions, but AI handles information synthesis and routine documentation, letting physicians spend more time on actual patient care rather than administrative overhead. Legal research is being transformed. Lawyers can query case law in natural language instead of learning complex search syntaxes. LLMs analyze contracts to identify problematic clauses, summarize depositions, draft initial document versions, and conduct preliminary research on novel legal questions. Associates spend less time on discovery and document review, more time on strategic analysis and client interaction. In scientific research, these models help synthesize findings across thousands of papers, suggest experimental designs, generate hypotheses based on existing literature, and even write first drafts of methodology sections. They're particularly valuable in interdisciplinary work, helping researchers understand adjacent fields and identify relevant research from domains they're less familiar with. We need to talk honestly about where these systems fail, because understanding limitations is just as important as understanding capabilities. And there are both practical limitations that might be overcome with better engineering, and fundamental constraints that stem from how these systems work. First, let's address hallucination, the tendency of LLMs to confidently generate plausible-sounding but completely false information. This isn't a bug exactly, it's an inherent feature of how these models work. Remember, they're predicting probable text based on patterns, not retrieving verified facts from a database. When asked about topics outside their training data or required to generate highly specific information, they'll often fabricate details that fit the expected pattern. The danger is that these fabrications are delivered with the same confident tone as accurate information. The model doesn't know what it knows versus what it's making up, it's just generating high-probability token sequences. Users need to verify important information independently, especially for domains where accuracy is critical, like medical advice, legal guidance, or technical specifications. There's also the consistency problem. Ask the same model the same question twice, and you might get different answers due to the stochastic sampling process. More concerning, ask logically equivalent questions phrased differently, and you can get contradictory responses. The model doesn't maintain a consistent world model, it's generating responses independently based on immediate context. Reasoning limitations deserve attention. While LLMs can handle impressive logical tasks, their reasoning is fundamentally pattern-based rather than symbolic. They struggle with problems requiring precise multi-step logic, especially when those problems differ from training examples. They can appear to reason but break down on edge cases or when you probe their understanding with subtle variations. Mathematical computation is a particular weakness. These models haven't learned arithmetic by understanding numbers, they've learned it as token patterns. Simple addition works fine because they've seen countless examples. But unusual calculations, especially those involving large numbers or many steps, often fail. They're doing fuzzy pattern matching, not precise computation. Context window limitations, while improving, remain a constraint. Even models with 100,000 token contexts can't truly process that much information with equal quality throughout. Attention patterns tend to focus on recent context and explicitly highlighted information. Details buried in the middle of very long prompts often get missed or underweighted. There's also the temporal knowledge cutoff. Models only know what was in their training data, which ended at a specific date. They have no inherent awareness of current events, recent developments, or any information published after training. Some systems address this through retrieval augmentation, connecting to search engines or databases, but the base model itself is frozen in time. Bias is perhaps the most socially consequential limitation. These models learn from human-generated text, which contains human biases around gender, race, culture, politics, and more. The training data includes everything from carefully edited encyclopedias to random internet comments. Biased patterns in this data get encoded into model parameters. This manifests in subtle ways. Word association tests reveal stereotypical connections the model has learned. In scenarios involving people, the model might make biased assumptions about roles, capabilities, or characteristics based on demographic factors mentioned in the prompt. Even attempts at debiasing during fine-tuning can't fully eliminate patterns baked in during pre-training on vast, unfiltered datasets. There's also what I call the capability confusion problem. These systems are simultaneously highly capable on some tasks and surprisingly incompetent on others. They might write eloquent poetry but fail at basic spatial reasoning. They'll explain quantum mechanics but struggle with common-sense physical intuitions a 5-year-old has. This uneven capability profile makes it hard to build reliable applications. You're never quite sure where the model will fail. Adversarial brittleness is another concern. Small, carefully crafted changes to prompts can dramatically change outputs in unexpected ways. These models don't have robust understanding. They're navigating a high-dimensional probability space where similar inputs can lead to very different outputs. Malicious users can exploit this through prompt injection attacks or by finding adversarial examples that cause misbehavior. Privacy and data leakage present genuine risks. Models sometimes memorize specific training examples, especially ones they saw repeatedly. Prompted correctly, they might reproduce email addresses, phone numbers, or other sensitive information that appeared in training data. This isn't hypothetical. Researchers have demonstrated extraction of training data from deployed models. Energy consumption and environmental impact deserve mention. Training these massive models requires enormous computational resources, translating to significant carbon emissions. Even inference, running trained models, uses substantial energy at scale. As AI systems proliferate, their environmental footprint becomes a legitimate concern. Now I want to venture into more philosophical territory, because large language models force us to confront deep questions about the nature of intelligence, understanding, and perhaps even consciousness. These aren't just abstract musings, they have practical implications for how we develop and deploy these systems. Let's start with the symbol grounding problem. Philosopher John Searle posed his famous Chinese room thought experiment. Imagine someone who doesn't speak Chinese sitting in a room with an instruction manual for manipulating Chinese symbols. They receive Chinese characters, follow the manual's rules to select response characters, and pass those out. To an outside observer, it looks like the person understands Chinese. But they're just manipulating symbols without understanding meaning. Large language models are arguably sophisticated Chinese rooms. They manipulate token embeddings according to learned patterns without any grounded understanding of what those tokens refer to in the physical world. They've never seen a cat, felt rain, or tasted chocolate. Yet they can discuss these experiences in ways that seem to reflect understanding. But here's where it gets complicated. Does grounded experience actually matter for functional intelligence? If a system can reason about concepts, make predictions, solve problems, and communicate effectively without sensory grounding, does it matter that it lacks subjective experience? We're forced to distinguish between phenomenal consciousness, what something feels like from the inside, and functional intelligence, the ability to perform cognitive tasks. This connects to questions about intentionality. When you have beliefs, they're about something. Your belief that the sky is blue is about the actual sky. Philosophers call this aboutness, intentionality. Do LLM representations have genuine intentionality, or are they just structural patterns that we interpret as being about things? When a model processes the token, cat, is that representation really about cats, or is it just a learned pattern of associations? You might think this is pedantic philosophy, but it matters practically. If LLM representations have genuine intentionality, then their outputs carry meaning independent of human interpretation. If not, then we're essentially projecting meaning onto sophisticated pattern matching. This affects how much we should trust these systems, what rights or protections they might deserve as they grow more sophisticated, and whether we're actually making progress toward general intelligence or just building better statistical mimics. There's also the question of emergent capabilities. As models scale up, more parameters, more training data, more compute, they suddenly gain abilities they weren't explicitly trained for. GPT-3 could perform arithmetic despite never being explicitly taught. Later models show rudimentary reasoning, theory of mind, and ability to generate code in languages barely represented in training data. These are emergent properties arising from the complexity of the learned representations. This emergence suggests that intelligence might be less about having the right specialized modules and more about sufficient scale and richness of learned representations. Perhaps consciousness itself is an emergent property that appears when information processing systems reach sufficient complexity. Or perhaps there's something fundamentally different about biological neural networks that silicon ones can never replicate. The Chinese room thought experiment has a potential counter, the system reply. Yes, the person in the room doesn't understand Chinese. But maybe the entire system, the person plus the manual plus the room, collectively understands Chinese in a real sense. Similarly, maybe understanding in LLMs is a property of the entire trained system, not localizable to any particular component. The meaning isn't in individual parameters or attention heads, it's in the collective behavior of billions of parameters working together. There's also interesting parallel to human cognition. You presumably believe you understand language, have genuine thoughts, and possess consciousness. But neuroscience tells us your brain is biological cells passing electrochemical signals according to physical laws. There's no special consciousness fluid or soul stuff. So how does subjective experience arise from objective neural activity? We don't know. And if we don't understand how meaning and consciousness emerge in biological brains, can we definitively say they can't emerge in artificial systems? These questions become urgent as we consider future development. If we create systems that genuinely suffer or have interests, we'd have moral obligations toward them. If we build superintelligent systems without understanding what they actually understand, we might be unable to predict their behavior. Philosophy becomes practical in the age of AI. Let's turn our attention to where this technology is heading. Understanding current trends and likely near-term developments will help you anticipate what's coming and prepare accordingly. The most obvious trend is continued scaling. We're seeing models grow to trillions of parameters, trained on ever larger datasets with more computational resources. There's debate about whether this scaling alone will continue yielding improvements or whether we're approaching diminishing returns. But for now, bigger models trained on more data with more compute keep demonstrating new capabilities. However, pure scaling faces practical limits. Training costs are already measured in tens of millions of dollars for cutting-edge models. At some point, economic constraints will force different approaches. We're already seeing research into more efficient architectures, better training algorithms, and ways to get more capability from smaller models. One promising direction is sparse models and mixture of experts. Instead of every parameter activating for every input, these architectures learn to route different inputs through different subsets of parameters. This allows increasing total model capacity without proportionally increasing per inference compute. You get something closer to specialized experts collaborating rather than one generalist processing everything. Multimodal models represent another major frontier. Current LLMs process text, but the world isn't purely linguistic. Next-generation systems combine language models with vision encoders, audio processors, and potentially other sensory modalities. These multimodal systems can analyze images, generate pictures from descriptions, understand video content, and integrate information across modalities. This multimodal capability addresses some grounding problems. When a model can process both the word, cat, and images of cats, its representations potentially gain richer meaning. It's learning associations between linguistic symbols and perceptual patterns, moving closer to genuine grounded understanding. We're also seeing development of models with stronger reasoning capabilities. Current LLMs do pattern-based reasoning, but research is exploring hybrid systems that combine neural networks with symbolic reasoning engines. These systems might maintain explicit logical knowledge bases alongside learned representations, allowing them to perform precise logical inference while retaining neural networks' flexibility and generalization. Retrieval-augmented generation is becoming standard. Instead of relying solely on parametric knowledge baked into model weights, these systems query external databases or search engines during inference. When asked a question, they first retrieve relevant documents, then generate answers conditioned on both their training and the retrieved information. This helps with factuality, current events, and reduces hallucination. Personalization is another trend. Future systems might maintain persistent user models, learning your preferences, communication style, and knowledge gaps over time. Instead of starting fresh each conversation, they'd accumulate context about you, providing increasingly tailored assistance. Privacy concerns need addressing, but the capability advantages are clear. We're likely to see increasing specialization. Rather than one general model for all tasks, we'll have ecosystems of specialized models optimized for specific domains or applications. A coding assistant, medical advisor, legal researcher, creative writing partner, each fine-tuned and architected for its purpose. The challenge becomes orchestrating these specialists and knowing when to invoke which. Agent-based systems represent a paradigm shift from chatbots to autonomous assistants. Current LLMs are reactive, they respond to prompts. Future systems might proactively monitor your workflow, suggest relevant information, break complex goals into subtasks, and coordinate actions across multiple tools. Imagine an AI that doesn't just answer questions about project management but actively helps manage your projects. Safety and alignment research is intensifying. As these systems grow more capable, ensuring they behave in accordance with human values becomes critical. We're seeing work on value learning, interpretability, robustness to adversarial inputs, and reliable truthfulness. The goal is systems that are not just powerful but also trustworthy and aligned with human interests. Regulatory frameworks are emerging. Governments worldwide are beginning to address AI through legislation. We'll likely see requirements around transparency, testing, liability, and safety standards. The regulatory landscape will shape which applications are permitted and what safeguards are required. Economically, we're heading toward AI becoming infrastructure, ubiquitous, essential, and mostly invisible. Just as you don't think about database technology when booking a flight, you might not think about the LLM powering your daily tools. AI capabilities will be embedded in every software application, quietly enhancing everything from email clients to spreadsheets to design tools. So here we are, at the end of this deep dive into large language models. We've journeyed from the fundamental architecture of these systems through their training processes, explored how attention mechanisms and embeddings enable their capabilities, examined their real-world applications and limitations, and even ventured into philosophical questions about the nature of intelligence itself. What should you take away from all this? First, a more nuanced understanding of what LLMs actually are. They're not magic, they're not conscious, and they're not infallible oracles of truth. They're sophisticated statistical models that have learned rich representations of language patterns from vast training data. This makes them incredibly useful for many tasks while fundamentally limited in ways we need to respect. Second, I hope you've gained practical insight into how to use these tools effectively. Prompt engineering isn't about tricks, it's about understanding the model's inference process and crafting inputs that guide it toward useful outputs. Be specific, leverage learned formats, request step-by-step reasoning, provide examples when possible, and iterate based on results. Third, maintain appropriate skepticism and verification habits. These systems hallucinate, reflect biases from training data, and can be confidently wrong. For consequential applications, always verify outputs independently. Use LLMs as powerful first draft generators and research assistants, not as final authorities. Fourth, recognize that we're still in the early stages of this technology. Today's systems, impressive as they are, likely represent a small fraction of what's coming. The trajectory points toward increasingly capable, multimodal, specialized, and integrated AI systems that will reshape how we work, learn, create, and solve problems. Finally, stay engaged with the ethical and societal dimensions. These technologies raise genuine questions about labor displacement, misinformation, privacy, bias, and the concentration of power. We all have a stake in how AI develops and deploys. Being informed, asking hard questions, and demanding responsible development isn't optional, it's necessary. The large language models we've explored today are simultaneously profound achievements and works in progress. They're useful tools with significant limitations. They're statistical systems that somehow capture aspects of meaning. They're transforming industries while raising troubling ethical questions. Holding all these tensions simultaneously, understanding the technology deeply while maintaining critical perspective, that's the challenge for anyone navigating this AI-transformed world. Thank you for taking this journey with me. I hope you've gained not just knowledge about LLMs, but a framework for thinking about them that will serve you as this technology continues to evolve. Stay curious, stay critical, and keep learning. Because whatever the future of AI holds, understanding it deeply will only become more important.